Hello and welcome back, everybody. Today we're going to do something really interesting but also really challenging, at least for me. We're going to try to do some ray tracing and see. And I've already had a quick look and found out that ray tracing involves quite a bit of math and geometry. And there are practically two ways. We could either simulate rays and check if they hit an object, and if they do, then they are blocked by that object and cast a shadow. The alternative would be to define objects and their shapes and calculate tangents based off that, or based off them. So let me just pull something up. External tangent of circles. So that is also something we could do. That would probably be the computationally more efficient thing to do. So we could draw two circles and cast a shadow using the tangent, the so-called external tangent. Yeah, but let's see. So my goal in this episode is to, let me pull up Paint for a second and make this black. So I would like to have two circles. For example, this one, a small one, the small one, and a bigger one. And I would like the smaller one, actually the size doesn't matter, but I would like one of them to be a source of light and cast light into all directions like that, just like a mini sun or a light bulb. And then I would like to make the entire screen bright. Let me just do that. For example, like that. Well, let's use a gray. And cast a shadow behind the object that is blocking light. For example, here it would look like... come on. Here, this would be the shadow. And maybe that would be the shadow. Something like... well, something like that, maybe. And then the shadow area should be black. Yeah, you get my point. This should be the shadow then. And what's the point of that? Why do we even do that? Well, somehow in the recent time, in the last couple of videos, we have done quite a bit of game engine fundamentals, and casting shadows is of course one of the most important parts of modern graphics. So why not have a look and try to do it ourselves? So I really have absolutely no idea where to start. So I always start with a standard IO import, because sooner or later we will need standard IO. I'm going to save that file into raytracing.c. And also one thing to note is that I would like to be able to pull the light source around on the screen. So this is going to be an interactive simulation. It's not just going to be a generated image. Yeah. Okay, standard IO, great, perfect start. So then let's continue with a main method. We're going to need that one anyways. We don't need any import arguments. And we are going to use for graphics includes SDL2. And aside from that, I think we should be fine for now. Maybe we're going to use math later. But for now, let's just ignore that. Let's call SDL init and initialize SDL. That's just a call that you do whenever you start coding SDL. SDL consists of many subsystems, for example, video, audio, whatever, and we are just going to use video because we're rendering graphics. Then we're going to create an SDL window, and that is going to be done using the call create window, and we're going to call that window ray tracing. Then, if I remember correctly, then we pass x, y coordinates, and we can center the window using SDL window pos centered like this, and we can center the y coordinate as well, and then width and height are going to be 900 by 600, but I'm going to create some global constants for that. So let's define width and height for the window here. This way we can also change width and height later quite easily. So that is our window. Of course, the pointer declaration at the end of the variable name is wrong. I have to do it here. And that is it. Also, we have to, by the way, don't be shocked right now. I know how to do this because we do this practically at the start of every video. But if you are not familiar with SDL, don't worry about it. This is the blueprint start of practically every SDL application. So this is just something you get used to by doing it over and over. And then the interesting stuff comes when you render your own graphics, and we will do this in just a few seconds. But for now, we're just creating a new window so that we can have a starting point. The next thing to do is, well, just let me show you, just in case you are new to SDL. Let's create a delay here. And now we should be able to compile this. And I need to adapt my compilation command a bit. I'm just pulling up a compilation command from one of the last projects. And it's going to be, the file name is called raytracing.c. Yeah, so we're going to create a ray tracing binary. What did I do wrong here? So I'm calling the compilation command cc. The output file is ray tracing, and the input file, the source code file is raytracing.c. And then I'm passing a couple of flags which are probably not needed in this project. I only need SDL for now. So this should do it. But there's an error. And the error is create window is obviously wrong because it's an SDL function. So this is going to be SDL create window. Oops. SDL create window. And I forgot passing flags at the end of this command. We can also pass flags to this window creation command. For example, we can define whether the window should be full screen, whether it should have borders and stuff like that, but we don't need it right now. So let's just execute the ray tracing application. Wait, did I compile? Yeah. And let's execute that and see how it looks like. So we have an empty window. The title is ray tracing, and the window surface is black. So the black part of the window is black. So let's change that by retrieving the surface. And we always need the surface in case we want to draw anything. So let's do a get window surface. There it is. And we can just pass the window in and access the surface like this. So it still compiles, so that is good. And what is up next? Next we can draw something to the surface. So let's use the function SDL fill rectangle. That is when you want to draw pixels or draw larger areas of pixels, for example, rectangles. Actually, everything that we're going to draw is based on simple rectangles. Even the circles, we're going to render them ourselves. And we're going to fill this rectangle on the surface. We're going to pass a rectangle, an address of a rectangle object. We're going to create that in a second. And we're going to pass color white, which is also a constant that we're going to define here. Color white. And color white is that Did I do too many Fs? FF, 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 FF. And the rectangle is going to be this right here. And we're going to initialize this structure as follows. We're going to pass X and Y coordinates. For example, let's just do 200, 200, 200, 200. So we pass X, Y, and the width and the height of the rectangle. So it's going to be a square. Let's compile and execute, and we can't see anything yet because I missed updating the surface. So right now we've written this rectangle into memory, but STL is not displaying it yet. So we have to call update Windows surface. Oh, there's a Windows surface rects function. Don't know what that is. I've always used the update Windows surface. And I have to pass the window here. But I would like to look up what the other function is. Yeah, so that is the basic of our graphics stuff. So now we have a window, it contains a rectangle, and everything else is based on this simple approach right here. If you want to draw a circle, then all you do is you render thousands or hundreds of small rectangles that make up a circle. If you want to create a moving rectangle, then you draw the rectangle and then you loop over it and draw it in different positions. So everything is based on this small code snippet you can see here. This is very simple. And that's why I like C a lot. That's why I like STL a lot. It's just, well, you get just what you need and not more, and you can figure out everything yourself. Of course, there are also some more advanced functions in STL. For example, a renderer and this kind of stuff, but we're not going to use it. That's not the fun of the whole thing. So let's have a look. I was just curious about this one method. The fill, what was it called? Update window surface with rects. Update window surface rects. Copy areas of the window surface to the screen. Aha, this is interesting. So this right here updates the window surface within a certain rectangle, I think. And this might, I hope I understand it properly, but I guess this is for efficiency. So if you want to redraw something on the screen, you don't have to redraw the entire screen, but only that rectangle. Yeah, you reflect changes to portions of the surface on the screen. We're not going to need that. We're just going to keep things very, very simple. And the next thing that we are going to do is we're going to create a loop and animate the rectangle for now. Or no, let's not do that. First of all, we should create a circle. So to do that, let's create a new method that is going to be called fill circle. Fill circle, and we fill the circle on the surface, and then we can also pass a color. And I'm thinking, is anything else needed? Yes, we are going to also initialize a circle structure to define the circle. So a circle consists of an x coordinate, a y coordinate, and a radius. Why do I use the double? I use that because when we move the circle according to specific mathematic formulas or whatever, then using integers here would propagate errors over time. So whenever you render something, whenever you model some data in the backend, if you have the memory and the CPU capacity to do it, always use doubles. If anyone objects, please put it in the comments, but I've found this to be better working than integers. So we have the circle right here, and we're going to create a method that is void. It does not return anything, and we're going to call it fill circle. It fills a circle to an SDL surface. And we're going to pass that in, and then we're going to pass the structure circle circle. It does not need to be a pointer because we can just pass by value. We don't need to modify the circle itself. That's why it can just be the regular structure, data structure. And to fill the circle, yeah. And that is interesting. We have already done this in one of the last episodes, the bouncy ball episode. So if you're interested in more detail there, have a look at that. But let me just create a new, or is there more space here? Yeah, let's create this drawing area right here. I'll make it black. Let's zoom right in here. And we're going to create a circle. And as you can see, the circle is already confined within a square. And what defines a circle? Pretty much, a circle is defined by its center point. Let's say this right here is the center point, and then it has a radius. Actually, that is enough to draw a circle. And for every pixel on the screen, you basically check, is the distance from the center point of the circle smaller than the radius? And if yes, then color that pixel. To draw it more efficiently, we can also limit the search the search of pixels that are within the circle to this rectangle, because any pixel outside of this rectangle, for example, all the pixels here, they are not going to be inside the pixels. So we can check this rectangle, and this rectangle starts with, well, this right here is the x minus radius. Well, okay, let me put it like that. This is x is 0, at least from the circle's perspective. Then this right here is x minus radius, and this right here is x plus radius. Oh, well, it doesn't matter if x is 0 or not. So this is the x coordinate of the center point. So we check from x minus radius to x plus radius. Is the pixel within the circle? And we do the same for y minus r down to y plus r. And this right here is y equals 0. So let's just quickly do this and check if we can render a circle to the screen. So all we need to do is we need to loop over. I think we should we use doubles here? Yeah, let's just use doubles here as well. I don't know if it works. I think it works. So double x, and x starts at circle dot x minus circle dot radius. So that is what we have figured out here. And then we loop over all x coordinates up to this one. I'm doing this a bit differently than last time, but let's see if this works. I think it will work. And then we will loop up to x smaller than x circle, or smaller than or equal to circle dot x plus circle dot radius. Okay. And then we can loop over the y coordinates. Let's just do that. Y is equal to circle. I guess we can just copy this. Let me just try and copy this, indent it like that, and then we can jump to the X, change it to a Y, jump to X, change it to Y. Let's see, I'm just practicing a bit of Vim. Yeah, okay, I hope I didn't cause a bug right here. Because whenever I copy and paste something and just change the variable name, there's going to be some bug. But I think this is okay right now. We haven't, yeah, come on. We need to specify the radius here. Or I will just rename this to R. This makes the code a bit shorter. So what is the error here? Expected semicolon. Why? Yeah, of course we also have to increment X after all of that. And here let's do Y++. And now inside that loop, we can just fill the pixels of the circle. No, we can't yet fill the circles of the pixels of the circle because we are looping over X and Y coordinates, but those are the X and Y coordinates of the encapsulating rectangle. And now we have to check whether the X and Y coordinates are even inside that circle. To do that, we have to create a new double that is the distance from center of the circle. So we check the pixel distance from the center, and that is going to be the square root actually, but yeah, we don't need the square root if we calculate this distance squared. Okay, so this is going to be X minus circle X multiplied by X. I was trying to avoid the math library, but let's just do it properly here. Actually, yeah, let's import it and let's use the pow function to do that. And we're going to use X minus circle X and that to the power of 2 plus, I think there should be a plus right here, and then let's do Y minus circle Y to the power of 2. So that is the distance squared. To get the distance, we would have to draw the square root of that, but we don't need to do that. I'm just saving computational power, especially because we're looping over all the pixels here, and we're going to animate this, and this is just unnecessary computation. So let's just continue with the distance square, and we can check if the distance squared is bigger than the circles. Oh no, let's do circle. If the distance squared is bigger than the radius squared, and to not have to compute that over and over, I'm just going to introduce a new variable here that is the radius squared, and that is equal to circle R and then power 2. And so if the distance squared is bigger than or smaller than the radius squared, then we can fill that pixel. So that is done using a rectangle. We always have to use rectangles in SDL, but that rectangle is going to reflect an individual pixel, and an individual pixel has the size 1 by 1. So this is a very small rectangle. So the size is 1 by 1. What else is there? No, X, Y. Those are the coordinates of the pixel we're dealing with. And 1 by 1, width and height. So that's the pixel we're going to draw. And we're going to fill it to the screen or to the surface here. Pixel, and it's going to be color white. Actually, we fill the circle and we pass a color into it. So let's use the passed color. And I forgot introducing that color up here. And the color is a 32-bit integer, an unsigned integer, and that data type here, that uint32, that is coming from SDL. So I'm not making this up. And right here we have to pass the address of the pixel, not the pixel itself, or not the pixel value. Okay, so we fill a pixel to a surface, and we fill a circle to a surface, so that we have to pass the circle here as well. And we haven't defined the circle here yet, so let's just create a structure. Circle, circle, and that is going to be our... That's going to be x, y. Let's just also do 200, 200, and the radius is going to be whatever, 80. Does that render? Yes, compile. I'm becoming confused. Okay, and we're filling that circle now using our utility method right here. And there's still an error according to the compiler or the linter. There's a semicolon expected, and that's the semicolon up here from the struct. Okay, let's see. I would expect now a circle to be drawn. Is it not working? Oh, there's an error. What is the error is we have to now include the math library, because up here we included math.h, and for most compilers that can be done using a simple -lm link math library. Oops, -lm. And that's a circle. As simple as that. Awesome. Okay, and now all we have to do is, or something that we have to do is we have to be able to draw that circle using the mouse. So let's try to do that. To get any movement in SDL, we have to restructure our main method a bit. So let's create a loop, a while loop, and we're going to loop over stuff right there. Because to animate something, we have to do something over and over and over. We have to redraw and redraw and redraw. We're going to call inside that loop the fill circle and the update window, and we're going to use a delay, but we're going to use a much smaller delay. So let's try to do 20, for example, or 10, it doesn't matter. 10 would correspond to a frame rate of 100 frames per second, because 10 milliseconds, multiply that 100 times and you have 1 second. Okay, what is the condition to break the loop? The condition to break the loop is a new flag that is simulation running, and that is true. And while the simulation is running, we are looping. However, we also want to be able to cancel that loop, so we have to check for key presses using an SDL event. And that's something that we are going to read in another loop. That is the so-called event processing loop or something like that. And here we do SDL poll event. So we are listening, or we are reading all the events. We're reading all the events, and the values are going to be written into the event variable. And then we can do the following. we can check what kind of event we now have. So if the event type is equal to SDL quit event or SDL quit, then we can. And by the way, SDL quit is the event that is thrown if I press the X icon on the small window. So that is the regular way of quitting an application. So if anyone quits the application, we have to stop the simulation by setting the simulation running to false, and then we're going to exit this while loop, and then this while loop is going to be exited as well, and the application is going to be finished. So let's see. We still don't have any movement here because we don't update the circle, obviously. But if I press the X icon, then we can quit this. If we hadn't done this event processing right here, we wouldn't be able to quit the application, which is quite funny because it's, you have to then to go to the processes and kill the process individually, and it's not good. Okay, so another event that I would like to listen to now is a mouse event, because now I would like to drag the circle along the screen. So let's pull up some documentation here and look for maybe the event, what is there? So we just use this poll event function right here that is polling for currently pending events. And events are basically everything from mouse events, keyboard events, joystick events, whatever. And we are retrieving a value into the SDL event structure right here. And this event structure is actually quite funny. It consists of a ton of different fields, and we can just read the field that we need. So before we were just reading the type, and that was SDL quit. But now we want to get some more detailed information. For example, what happened on the keyboard, or what happened with the mouse. So where is that? Where's the mouse? Mouse motion event. That sounds good. So let's look for SDL mouse motion event here. So we can access that by calling event.motion. So let's just do that. I'm just calling event.motion. And on that motion event, we could check the type. We have to check the type. So let's just make sure that the event, the type is SDL mouse motion, and then we have to make sure that I would like to drag the circle when I click the mouse. So I have to, there's the X coordinate, the Y coordinate, that's already important. But what is the mouse state? I think this is it. The current button state. So the button is the mouse button. So if that is clicked, if there's a mouse click, then state should have a non-zero value, I suppose. So let's just check, and event motion state is non-zero. Why is this not? It is compiling. So if the mouse is clicked and the event type is a mouse motion, then we can get from the motion event the X coordinate, and then we can set the circle X coordinate to that mouse coordinate. And then we can do the same for the Y coordinate. Why doesn't it work? I'm just trying to search the... Ah, okay. I'm struggling sometimes with Vim, but I'm managing it. Okay, so we have updated the circle X and Y values, and then we're filling the circle here. So maybe it's already working. Let's have a look. I'm compiling, I'm executing. Oh, and I can do something, but the issue is that the circle before, the circle from the frame before is not being erased. So before I fill the circle, we have to do another fill rectangle and recolor the screen in black. Fill rectangle. And we're going to pass a surface, and we're going to pass an erase rectangle, and the erased rectangle is practically a black rectangle that covers the entire screen. And we pass color black here. So we redraw the screen in black. Let's define color black up here. Color black 0x00000000 like that. And the erase rectangle, let's define that up here somewhere, because that is going to be the same. That's pretty much going to be a constant, actually. Can we define a rectangle as a constant? Let's just try it. I have no idea if that works. Erase rect, and that's going to be an SDL. Ooh, I have no idea if this works. No. That just feels wrong. Let's define that erase rectangle here. SDL rect, erase rect, and that is going to be equal to X and Y are 0, because we have to cover the top left corner, and then width and height are going to be the screen width and height, and that should be it. Oh, does that compile? I'm used to also cast this, but apparently it works without. Let's see. What is the warning here? Fill rectangle receives the surface, the rectangle, and color black. Isn't that correct? Why am I getting a warning? Ah, of course. I have to use SDL fill. Oops. SDL fill rectangle. So that is not working. And now we have our ray tracing window, and we can drag the circle along the screens. Yeah, that's perfect actually. And it's quite responsive. That's fun. Okay, and now I would like to draw a second circle, and that is the circle that's going to cast a shadow. To do that, let's define a second circle here. Let's call it shadow circle. And that's going to be sitting at, let's just put it at 500, 300, and make it a radius 120, so it's a bit bigger, or even 140, like that. But there's no second rectangle. Of course, there's none, because we are not drawing it to the screen. So let's draw the shadow circle as well. And we can do that using a second call to fill circle. And let's pass the shadow circle here. If I just set shadow rectangle, then sorry for that. Okay, it's quite big. And I would like it to sit a bit more on the right-hand side. So let's adapt the x-coordinate of that. So x is going to be 700. Yes. Or maybe a bit less. 650. Okay, now comes the interesting part. Now we have to cast rays. So how do we do that? As I thought in the beginning, there are two possible approaches. One would be to just brute force draw or simulate rays going out from the first circle, and then checking whether they collide with the second circle. The other one would be doing it properly using some math. But I think the first approach is actually the way it's actually done for graphics. I think this is more of a brute force approach. Yeah, we have to find out how ray tracing works, or what a good simple solution would be. Maybe just for no. Yeah, now it becomes interesting because now I really have no idea where to start. One starting point could be to draw lines going out from the first circle. And that may be the thing, what we're doing. So let's try to do that. Let's create a method that generates rays. So we're going to create a void method. Or well, how does it generate rays? We have a circle. Let's call that method rays. So we have a circle. The rays obviously depend on the circle itself, because they have to be emitted from the x and y coordinates. But then, apart from that, what else do they depend on? Nothing. But I'm just thinking of how to store the rays. Should they be somewhere in an array, maybe? Should a circle store its own rays? Or are the rays part of the ambient environment? That's the question for me now. Yeah, let's try to store the rays globally using or maybe here, somewhere here. First we have to define what even array is. As you can see, my brain is going back and forth on solutions. If we created a structure array, oops. If we created a structure array, struct array, then what would define the array? Since it's pretty much just a line, it would have an x and a y coordinate that defines, well, the coordinate at which it resides. Then it would have an angle, let's call that M. No, let's just call it angle for better readability for my dear viewers. And then a ray should have a starting point and an end point. It definitely has a starting point. XY. Let's call that start X. Or X start. XS, YS. And then does the ray end? Well, every ray has to end somewhere. Either it ends at an object or it ends at the border of the screen. So I think we can define X end and Y end. And let me just also write out the X start and Y start. And this should be a data structure that represents a ray. Yeah, it's not really straightforward. So we have a circle. Oh well, where do rays originate? They originate at... Actually, they don't originate at the circle, but at a point. Let me just visualize this for you. Right here, let's go over to this side a bit. So we are drawing a circle. Let me just pick a bit bigger brush. Like this. Well, this is an ugly circle. Like this. Or maybe let's use... no, come on. Let's just do that. And this is the center point. And from that center point, rays will emit in all directions. So actually what you would think is that the rays are being emitted from that surface, but what is actually happening is that they all come from that common center point. So to properly model the ray generation, maybe it's not... Yeah, maybe we should just define that they're coming from X start and double Y start. This would then make it a bit more generic because we don't only work with circles. Oh, well, no, in the case of a circle, they have a common starting point. But what about the case of a rectangle, for example? We're not handling this case in this episode, but here, for example, the rays would be emitted in parallel like that. So here the starting point would be a common y coordinate, or it's not. So this is not a starting point, but a starting line. So actually, maybe it makes sense to still pass the circle into that method. So let's just do it. Circle, circle, and the rays are going to be. The rays are going to be stored in an array. Rays array. Yeah. So we're also passing a ray array. Let's call it rays, and it has a size rays number. So then later we can adapt this to 1,000 rays, 100 rays, 10 rays, and see the different results for that. And let's just, or I think we don't need to even use that constant here. We can just do that. I think this is only required for 2-dimensional arrays to pass a constant there. So we are dealing with rays. Then but actually it would make sense to know the number of rays that is passed. Let's just make it a bit more explicit and pass that number. Then here we can use the rays number to set the number of rays. I'll just use 100 for now. And yeah. So back at this method right here, rays. Now we have to loop, in any case, we have to loop over all the rays that we want to generate. So for every ray, starting with int I is 0, I is smaller than rays number, I++, we do something. We have to generate a ray. And the ray is going to be, well, please note, one thing to note is that the array being passed into this method is empty. Okay, this is empty. We are using this method to initialize this array. So let's just call this generate rays. And then maybe for any ray that we're looking at, it's important to know the circle X position and the circle Y position. And well, what are we even doing here? What are we doing? So we have a center point. We want a ray to go out from that center point, but in which direction? We want different rays to go out in all directions. Like that. How do we know which angles those are? Well, we loop over all the angles. That's what we're doing. So we have to use an angle, double angle, and the current angle is going to be I'm just thinking how to define the angle here. Wait. That's such basic math, and I need to look it up. Line with angle. Math. Line equation with angle. Yeah. How can I find an equation of a line or draw a line given a starting point, length of line, and angle of line? Yeah, I'm totally aware of the m multiplied by x plus n is equal to y, but the problem is that m, what is m? Because looking at this coordinate system right here, x and y, if you have a line, then this right here is m. For example, here m is equal to 1. But if m is infinite, then m will just go up like this. So how do I even generate these kinds of m's? For sure I don't. That is probably the answer. Well, actually, one thing that we might note is that maybe we have to just generate angles from here to here, because this line will be one angle, then this, then this, then this, then this, and this covers also the left-hand side of lines. This is such a poor explanation, sorry about that. But I would like to do it a bit more elegantly. Line with angle, for example, 360. Yeah, right. This is 90 degrees. This is 180. That's clear, but how do I formulate this in an equation? How to plot lines with an angle between 0 and 360 degrees. Yeah, that's the question. Oh, what? How do we do it? Well, we can just do 360. We can just base our angle of 360 and do the following. I divided by race number multiplied by 360. And also here we would have to use the double I, because this should make the division a bit better. Oh, come on. Oh no. Maybe I can just cast it like this. So let's just see if we can at least generate angles. Print f angle. And then let's print a floating point number here and pass the angle into it. And don't forget the new line number here. Then let's compile that. I know we also have to call the generate race function. So we do that, for example, here. Generate race. And here we have a circle and a race array. We can just pass our circle and a race array. We haven't defined that one yet. So let's just go and do that. Struct race, that is an array of size number or race number. And we pass that into the method and we generate the race. So let's just compile that and execute our ray tracing binary, and and at least we are generating angles between 0 and 360, so that is good. As you can see, at least some intermediate results. But now maybe this is a completely poor approach. What is the sense of generating angles on a screen? Especially because the screen is based off X and Y coordinates that define pixels. So how does an angle help here? Is there maybe a better approach than that? There could be a better approach. So we have a screen. Let's just say that this is our screen. Then we have a center point. From that center point, well, what happens here? First, we generate an array that is defined by an increment in X and no increment in y. Ah no, that would be this line right here. Then if we generate another angle, another ray, we could do the same, but for a fixed y and 0x. Then another ray could be based off x and y are both incrementing, like that. And then more rays could be based off x and y are incrementing at different rates. But all those are, I think those are not, those don't make it easier to find the collision with other objects. So this is the angle between 0 and 360. How about defining the angle between 0 and 2 pi? Because 2 pi are also a full rotation. How do I get the math pi constant? Math pi constant in C. It's m underscore pi. M underscore pi. Undeclared. Does it compile? Let's see if it compiles. Yes, it does. So it's working. So that is the angle of the ray. Then, since we're just initializing the rays, let's just create a ray, struct ray, that is equal to, what do we pass into it? X start, Y start. X start and Y start are equal to circle X, circle Y. Then we pass an angle, and then we pass, well, we don't have the end coordinates yet. Do we even need an angle? I mean, the ray should be defined by start and end coordinate. Okay, we have to know where the end coordinate is based off the angle. Oh my god, why is this so complex? Circle X, Y, X, angle, end coordinate. Let's just make it 0, 0 for now. Whew, it's getting hot. No, wait. If we just ignore the X end and Y end for now, let's just ignore them. So then this is the ray. Then we can set the rays array at the current index to ray. So we are storing the rays. I think this should work. Yes, if I move this, nothing else happens. Okay. And we generate, where do we generate the rays? We generate them here. Let's remove that and let's generate the rays whenever we draw the circle. So then we update the rays. So let's see. when we compile and do ray tracing. And when I move the circle, I would expect the rays to be generated. Yes, okay, so that works. Of course, they also have to be generated up here somewhere at the beginning of the method. And now, what is actually important is to visualize the rays. So let's do a fill rays on the surface. We pass the rays, and then we pass a color. For example, color gray. And this is going to be the hardest part, because that's what I already thought about in the last couple of minutes and what was giving me a headache. But never mind, we can manage it probably. EF. Let's see. Now we need to create a new function that is called fill rays. Void fill rays. It's going to accept an STL surface because that's what we're going to draw to. And then we're going to accept a structure rays that has the size of number rays or rays number. And a color, uint32 color. So how do we call the ray? How do we draw the rays? It's really not straightforward for me. Why is this not straightforward? Let me just create a new rectangle here so we can draw on it. I will just misuse that part of the screen. Oh, of course, that doesn't work. Let me erase something. Okay. Okay. We have a center point. This is the center point. Now, we also have an angle. That angle is between 0 and 2 pi. So this would be the full 2 pi angle. Okay? So let's say this right here is the angle that we pass. And I would like to generate a ray that goes in this direction, like this, starting from the center point. Okay? How do we know to draw it in this direction given this angle? For example, this angle would be whatever, pi divided by, what is that? Maybe 3/2 pi or something like that. No, it's not. No, this is not it. This is an angle between 0 and angle and pi, because the full pi would be this right here. Draw angle between 0 and pi. The problem for me is not drawing it physically, but how to do that in the computer, how to do that in code. I don't get it. For example, if we have an angle of pi divided by 2, that corresponds to 90 degrees. That would be this line right here. How do we draw that? How do we know that x is going to be 0 forever and only y is going to increment or decrement, whatever? Well, actually, it's going down on the screen, but never mind. How do we know that? We would need a formula that tells us the first pixel is this one, the first pixel is this one, the second is this one, the third this one, and so on. So that means we would need two formulas. One for x and one for y. X at an index I, starting from the starting point, is equal to something. And the other formula must be y at index I, and then doing something. Since x is 0 for pi divided by 2, that would correspond to, well, wait. Let me use the color for x. We have x right here. This right here is a cosine. An ugly one, but this is a cosine. Cosine is 1 at 0. The value of cosine 0 is 1. That means actually right here for an angle of pi divided by 2, x is always 0. That means it corresponds more to a sinus. You know, the main part is whatever. This is a poor sinus, sorry. For sinus, angle 0 has a value of 0. So maybe x at this is sinus of the angle, and then, well, what is the I input even? Oh my god. xi Can we make this more simple? Maybe we define for x a new function that maybe we define for x the x increments per step. For example, a factor. For example, an angle multiplied by I. And then we do the same for y. Angle, but a different angle must be taken into account for y, I think. No. how maybe the question is, for a given angle, how much does x increment for every step and how much does y increment for every step? For a given angle, how much does x increment per step? For angle 0, x increments by a full step. That means that double x increment, or maybe double x draw, is well, we have to loop over all the rays. Let's loop over all the rays. If I manage to do this, I don't even know how I have a master's degree in all this stuff. I have no idea how I managed to do that. It's breaking my head, but okay, I have to admit that we didn't render rays to a two-dimensional screen. We did all kinds of integration, all that stuff, but not this. But this is really neck-breaking. So we are dealing with the first ray, struct ray is equal to rays at I. So we are retrieving the first ray. Then we access the ray. What properties does the ray have? X start, Y start, and angle. So obviously the drawn X must depend on the ray X start. That's no question. But then we also have to we have to loop over the individual ray to draw multiple pixels for it. And we have to draw that ray while end of screen reached, end of screen, or object hit. Oh, this is getting interesting now. And while not end of screen and not object hit, while this ray has not hit the end of the screen and not hit an object. And those are two new variables, int end of screen, that is 0, and int object hit is also 0. So we have to define that we want to draw X and we want to draw Y pixels. So X depends on the starting X, obviously. And then it's being incremented by I multiplied with maybe the cosine of the ray's angle. Because if the angle is 0, then we will draw along this axis. So that means I is fully incremented and Y isn't. So do we just copy this and apply the same formula to Y? I have no idea, but I think it's time to just try to visualize this on screen. And here we also draw individual pixels, so let's just copy the pixel drawing from up here and paste it down here. Oops. So here we have a pixel that is X draw and Y draw. I know those are doubles, but in the rectangle they should be then casted to a rectangle, so they are going to be integers. And yeah, let's see. I have no idea what's going to happen now. Okay, there's an error. Surface I made a typo somewhere. There it is, surface. Let's go back to the race methods. Okay, here we generate the race, and here we draw the race. I think we will get a failure because we don't try to stop drawing. This while loop will not exit. So maybe we should let's just try to exit this while loop at some point, because otherwise I will not be able to terminate the application. Let's do let's check if the end of the screen is reached. If X draw is smaller than let's check here. If X okay. If X draw is smaller than 0 or X draw is bigger than the width of the screen, then we hit the end of screen. End of screen is true. And then we also have to check for the height. If Y draw is smaller than 0 or Y draw is bigger than height, then end of screen is true. I think this is okay for now. Let's check what happens. Okay, this doesn't work, and I also can't exit it. Why? Ooh, and my processor is firing up. So let's create a new pane. Let's check the processes. And let's kill the ray tracing application here. This is the PID, the process ID, 1613. So yeah, now it's killed. So what was going wrong here? The problem is we are generating those X and Y values, but we are not incrementing I, so they don't ever change, and we never reach the end of the screen. So this has to be a new loop. Let's call it double step, and step is going to be 1. And this right here has to be replaced by step, and this as well. Then we have to make X draw depend on the previous X draw. So we increment it by the step, and we do the same for Y draw. And then we initialize both of them outside of the loop. So let's do double X draw is equal to circle. No, not circle. Ray X start. Was it X start or start X? X start. Okay, and let's do the same for Y. Y draw is equal to ray y start. And then of course we have to remove the double declaration here. Let's see. Okay, we still have no results, and I have to terminate that application in a secondary terminal 1706. Oops. So what's going on? I find it odd that I increment both of those by the cosine. Maybe one of those has to be sine. Because they can't increment at the same steps. But my reasoning here was for x is, or for the angle 0, x increments fully, but y... yeah, but y doesn't. So yeah, y has to be incremented by sine, so that's correct. So we check if any of those rays exits the end of the screen. That's correct. We can remove the generate... No. Wait, what are we even doing? In generate rays, we aren't... okay. We are generating the rays right here. We don't have to print the angles anymore, they are correct. And then we are filling the rays here. And it might be interesting to see what's going on inside that method. So we are looping over the rays. We are retrieving an individual ray. And we are checking if any of those, or we are drawing the rays. This method is just about drawing the rays. So it should be okay, actually. This has to be an AND. So let's see what this looks like now. Yes! Oh my god! Oh! That's so awesome. Let's see what happens if I move this. Oh my god, this looks so nice. This is really cool. And now we only have to check, we only have to check, this is probably going to last another hour, let's see. We only have to check if any of those rays actually hits this other ball right there. So the question is an object being hit? Actually, this should not be done in the draw method, in my opinion. So the question is, we generate rays from the circle, we receive a structure of rays. All of those rays originate at that individual circle. So here we generate the rays of that one circle, but we should also pass into that method other obstacles, actually. Or do we do that in fill rays? I am trying to figure out, well, so we are drawing rays here, and I would like to have the rays stop when they hit the other object, which makes total sense But how do we know that another object is hit? We draw a maybe we draw a pixel of the ray, check if it collides. Then we draw another pixel of the ray, check if it collides. Then we draw another pixel of the ray, check if it collides. Yeah, let's just do that. I mean, that's probably the simplest possible solution. And yeah, real ray tracing is probably much more sophisticated. Of course it is. But we are just trying to learn things here, and we can't learn things if we just make things overly complex. We have to stick to the basics. So, is an object hit? How do we know if an object is hit? So here we draw individual pixels, and we have to check if an object is hit. Now, how do we know which other objects are there? We have to pass an array of circles. Or let's just pass one circle. Maybe later we will extend this to multiple objects, but for now let's make a proof of concept. And if that works, we might be able to extend it, but let's see. Depends on how long this episode takes. So if the X draw is inside the other circle, how do we check that? Actually, we already have a method here to check whether a coordinate is within a circle. This right there. Let's copy that and go down. So we have a distance, let me just put something here, some comment here. Does the ray hit an object? Then the distance squared of that ray X draw to the circle, which is now called object X, squared, and here we pass Y draw minus object X squared. And if the distance squared is smaller than the radius squared, yeah, let's just calculate. Oh no, I'm thinking whether we should also, yeah, let's calculate the radius squared here. Radius squared is power of object, radius power of 2, like that. What's the problem with that? Struct circle has no member named radius. Didn't I use radius all the time? Is it? Ah, okay. No, I didn't. So now we're checking the radius squared of that other circle, and no, we don't need that. And if the circle is being hit, then we can break the loop, probably. Let's see. No, this doesn't work. Why doesn't it work? Too few arguments. Ah, of course, I have to pass the other circle, our obstacle circle, into the fill race. Let's call the other circle obstacle circle. have already called it shadow circle, so let's use that. Shadow circle. That compiles, and that is ray tracing. Yes, that's it. That's it, guys. It's working. Awesome. Now, what would be... yeah, I broke the application by drawing this circle inside this one, because now ray tracing... Well, obviously, the light is being emitted from this circle, so if I draw the light source into the other object, no light can be leaving this circle. That is obviously true. So this is really nice. How about we make the other circle now move as well? How about some automated movement? Just to prove a point that we can make this really nice. So the shadow circle is moving down. Let's create a new method. Move shadow circle. We pass the shadow circle into it. Shadow circle. Like that. And we pass the actual address of it. So we pass a pointer. And then we create a new method that is called void move shadow circle. We receive the structure circle shadow circle here, and it's going to be a pointer. And then I still really don't know how I figured out the ray stuff. I didn't even use math. Okay, I used sinus and cosine, but that's it. How did I do it? At the beginning of this video, I pulled up this Wikipedia article thinking that we have to implement this now, but luckily we don't have to implement it. Okay. So we move the shadow circle simply by doing shadow circle dot x. And we move that by 1, for example. We can adapt the speed later. And because it is a pointer, we have to use the arrow operator. No, let's just move the y coordinate. And then also... Do we move x? Should we move x? No, let's just move y. So, but the shadow circle then needs a speed. No. Oh, great. Okay, so let's introduce a... this is so hacky that I don't really like this. I just want to move the circle a bit, so let's not do this in its own method, but let's hack this into the main loop. I mean, this is not core functionality. This is just improving the visualization. So it's just making it a bit more fun to look at. So we fill the circle right here. We move the shadow circle here. How do we move it? We have to create a shadow circle speed. Oh well, let's call it obstacle speed in y direction. I'll set it to 1, and then we update the shadow circle y coordinate by this obstacle speed y. And if a border is being hit, for example, if shadow circle dot x is smaller than 0, no, if the y coordinate is smaller than 0, then it has hit the upper border. In this case, we can set the obstacle speed equal to whatever it was before, but we reverse it. Oops. And also, if the shadow circle y is bigger than the screen's height, then we can set the obstacle speed y. Then we also reverse the obstacle speed y. So this could be one if case. I'll just keep it 2 just for better readability. Also, let's let's just see how it looks like. Okay, now as you can see, what the hell? Of course, this doesn't work like this. We have to check if the y coordinate plus the shadow circle's radius is smaller than 1. And we have to do the same for the height here, shadow circle radius. So now it should be bouncing off the bottom border of the screen. No, did I compile? Yes, and this is proper ray tracing, I would say. And let's make this a bit better even by defining a ray color ray, and we make the rays. What is a good ray color? Hex color picker. I would say it should be something like that, maybe. Let's have a look. So that is the color of the ray. And then I would like to render much more rays. Oh, wait, before we do that, let's make the rays a bit thicker. Because here we're just rendering them to the size of a single pixel, but that is not really, it does not really fill the screen. Let's try it with 3 pixels. Maybe that's too big, maybe it's too small. We will see in a second. Let's have a look. Of course, I have to change the color gray to color ray, because we specifically use that color now to color the rays, nothing else. And yeah, as you can see, yeah, it's not good. This looks trashy. Oh, and also somehow something doesn't work. We have to do minus shadow circle R here in this case. So if we're going up, we have to check the minus radius, because minus is going towards the top. Okay, and also I found it quite ugly that the rays are colored above all the circles, so let's do it before that. Let's have a look. That looks much better now. Still, it's not really, well, it is technically ray tracing, as you can see. So it's working well. I would like to make this, I'm still not 100% happy with it, because I think that the shadow circle should be sitting a bit more on the left-hand side of the screen, a bit more centralized, so we can see a longer shadow. And maybe let's make the first circle smaller, so it is a small light source. Okay. And what else? What else do we do? I would say let's make the screen a bit wider. For example, 1200, so we can cast a longer shadow. Yep, that's good. And now, how about we define many more rays? For example, 1000. Yes. And this is really cool. And as you can see, the farther the ray goes, the more imprecise the ray tracing goes. And that is actually, well, how it works. How about, I would like to take this to the limits and see if we can trace 10,000 rays. Ooh, this is going much slower now. So this is very laggy. This is not good. It's working, but this is too much. So let's keep this at 1000 or maybe even 500. And let's make the rays a bit thicker again. Where was it? Pixel. There it was. Yeah, let's rename this to ray point, and then we're passing here the ray thickness, and we're defining the ray thickness up here, ray thickness, and that is going to be, for example, 5 pixels now. Let's see how that turns out to look like. Maybe it's too much. Okay, that does not even color anything. Why? I missed the second parameter here. Okay. Yeah, I'm just wondering how do I make this look better? I mean, this is pixel-wise precision, and the ray tracing is really working. But I don't really like these lines. All of these lines, they make it look very messy. It would be good to make the lines a bit blurry, but that's... How do we do it? Let's just introduce some blur, some very stupid, simple blur. For example, by filling a second rectangle here. Let's call the rectangle ray blur. And that ray blur is basically the same as the ray point, but it's drawn at ray thickness. Let's introduce a new double blur size. That is, let's just say it's equal to 1.5. And that is going to paint a slight blur by over or underlaying a second color. Ray thickness multiplied by... yeah, we have to do this ray thickness here. So we increase the ray thickness and pass the blur size into the rectangle initializer. So this is now the ray blur, and we have to define a blur color. blur color. And that blur color is also passed into this method. uin32 blur color, like this. And down here where we use the fill, or call the fill race function, let's also pass the color ray blur. And that is going to be a similar color, but maybe a bit... is the blur warmer? Maybe a bit darker. I'm not really good at picking those colors. Let me just pick this one, this color, but we can adapt it. Color ray blur. And it's this one. 0x, blah, blah, blah. Ooh, this looks messy. So the blur is not really working, at least not according to how I imagined it to be. Color ray blur. Let's have a look. Color ray blur is used here. Then here a color is passed. That is the blur color. Oh. Ray blur. No. I mixed up the colors, I think. Blur color. Color. This is looking odd. Why is this so weird? I am drawing the blur, and then on top of that I'm drawing the actual ray. The blur has a blur color and the actual ray has its color. I don't get what the problem is. Let's remove the blur again. Yeah, this is much better, but yeah, no idea. Then let's just forget about the blur. Let's reduce the ray thickness to 1 again. And this is the true ray tracing that we have implemented right here. There is some aliasing. Come on. There is some aliasing here going on. You will definitely see this in the video, these weird pixel-wise effects, these weird hallucinating effects. That is because we are drawing individual pixels, and yeah, that causes interesting effects, especially when we calculate the positions of those pixels using sine and cosine and stuff like that. That's why you also see these patterns in the rays. But that is technically our ray tracing. That is our light source. We have another object that receives the shadow and casts it. Well, it does not receive the shadow. What am I talking? Yeah, and I find this is a very cool project. I would like to wrap this up at this point. I would just like to make the obstacle speed a bit faster, just to see some faster action. Yeah, come on. This is probably too fast. Let's make it for some final demonstration. This is our ray tracing result. I hope you liked it. And I think it's cool. I really enjoyed that we can drag the light source along the screen and position it, and we have an obstacle that casts a shadow in whatever direction we want. The farther away the light source is, the narrower the shadow is. And if I make it very close to the obstacle, then the shadow is also adapting to that. So that's a very cool project. Fundamentals of ray tracing. If you have implemented ray tracing yourself once or whatever, if you know how to improve this, then please let me know. I find it quite hard to, well, how do we color the light here properly? Maybe we should, but this would need more post-rendering, whatever. I still find this is a very cool project. Yeah. If you enjoyed this, then leave a like, subscribe, and let's just have a look at one last demo. I just want to see the ray thickness 2, how that looks like. Yeah, this looks a bit better, but yeah, okay, there's definitely room for improvement. It's still a fun project, so let's see you next time on this channel. And put your ideas in the comments, please. So far we have done so many different things. We have done Game of Life, we have done Pong, we have done 3D rendering, we have done some keylogging stuff, so hacking, encryption. Put your ideas in the comments. I always have ideas, but I would really like to hear from you what you would like to see. So let's see you next time. Bye.